We've been talking a long time about atoms. We've learned about the periodic table of the elements, electronic structure, energy levels, electron configurations, tons and tons of details. There's a lot to learn about atoms. Well, today we're going to take the next step and talk about how atoms, very, very rarely, is an atom on its own, or even an element on its own with its friends of the same element. More often, when an element exists in the world, it's going to come together with another element. They bond, okay? And that's called chemical bonding. So today's lesson is an introduction to that. Now, in order to be ready for this lesson, it's very important that you have some review of the stuff we've talked about before. So what I want you to do is pause the video in a moment, and I want you to draw Lewis dot structures for these elements right here. I've given you the numbers from the periodic table. And once you're done with that, go ahead and hit play again, and then I'll tell you the answers. Alright, so you've paused the video. You might have had to look backwards in your notes to remember what a Lewis dot structure is. And as you can see from my screen, you've had a periodic table up on your screen to help you. So rubidium number 1 is right here. It's number 37, and it is in group 1. So that means rubidium has one valence electron. And so we put 1 dot there. And remember, the valence electrons are the ones in the outside shell. There are many layers of electrons in rubidium, 5 layers to be specific. And in that 5th outside layer, there's 1 electron. Bromine is number 35. That's right here in group 17. If it's in group 17, that means it has 7 valence electrons. So I put 7 dots in the Lewis dot structure. Xenon is in group 18 right here. So xenon is going to get 8 dots because it has 8 valence electrons. Helium is number 2. Now helium is our exception element. It is in group 18. But helium only has 2 electrons total, so you should only put 2 dots on there. Every other element in the noble gases has 8 valence electrons, but helium doesn't. Helium only has 2. Okay? And finally, phosphorus is in group 15. It is also number 15, so phosphorus has 5 valence electrons. And I've clumped them all onto one side. And that's it for the warm-up. Okay, so chemical bonding. If you think back to one of our recent lessons, we spent some time talking about trends on the periodic table. Okay, there were trends for the radius. That was the first one we talked about, and how in the lower left corner, those are the biggest elements. The upper right corner, those are the smallest elements. We've got ionization energy trends. There's these patterns, okay? And one of them that we talked about was reactivity. So I'm going to go ahead and I'd like you to follow along in your notes. We're going to take a few notes. So recall our reactivity trend. And you'll have to do a quick and dirty drawing of the periodic table here. But the basic idea for this trend was that if you split the periodic table between metals and nonmetals, then the trend goes this way to the corners, okay, where the corners are more reactive, with one exception, okay, and that is group 18. The noble gases are not reactive at all. In general, you can get some of them to react. I should let you know that, but for the most part, noble gases really are not very reactive. That's why they're called noble gases, right? They're the kings and queens. They don't associate with other elements, with commoners, right? So it's interesting to think, well, why is this? Why does this trend happen? Because we didn't talk about that when we were doing this concept. Why are the alkali metals so reactive, but the post-transition metals over here, they're hardly reactive at all? What's the big deal? Okay. Well, if you're paying close attention, maybe you'll notice that the closer an element gets to the noble gases, the more reactive it is. If we look at the halogens here, fluorine, chlorine, bromine, iodine, these are the most reactive of the nonmetals. Fluorine is ridiculously dangerous. Fluorine gas, kill you in a second. Same with chlorine gas, totally deadly. And they're right next to the noble gases. Alkali metals, you might think, well, those are as far away as you can get from the noble gases, but really, no, they're not. They're only one step away. Look at sodium, for example. If I put a piece of sodium metal into water, usually it'll start that water on fire. That's pretty reactive. Well, sodium is number 11, and only one element less, number 10, is neon, a noble gas. So you see sodium, an alkali metal, is only one step away from the noble gases, just like the halogens. It's just going in the other direction. And these are the most reactive metals on the periodic table. So there's something about the noble gases, and it's almost like all the other elements on the periodic table want to be like the noble gases, and the halogens and the alkali metals are only one step away. They're so close they can taste it. They really, really badly want to become a noble gas. So let's go ahead and add this to our notes. Okay, noble gases are not reactive. Halogens and, what did I say, alkali metals, they're very reactive. Okay, so elements don't actually want anything. They're not people, but I use that to help us understand. Okay, so I'm going to put that in quotes. Elements wish to be noble gases. Well, what is it that noble gases have that other elements don't? Why is this neighborhood so special on the periodic table? Well, we've learned this before. The noble gases are the elements with full shells. Every shell in a noble gas is full. Think about it. Helium, 2 electrons with only one shell. Well, the first shell is full with 2 electrons, so helium has a full valence shell. Neon is in period 2, so it has 2 rings, 2 energy levels. That second energy level has 8 electrons in it. Neon is in group 18. It has 8 valence electrons. 8 electrons is full for the second shell. There's something about having a full valence shell that elements really like. Okay, so elements wish to be noble gases because they have, and I'm going to use the word complete, that means full, they have complete valence shells. Why do we care about a complete valence shell? Always why. If you're a scientist, you always got to ask why. Why is a full valence shell a big deal? Well, it's more stable, okay? This is more stable. Everything in the universe, you experience this in your own life. Everything in the universe goes toward a state of more stability. If you pour yourself a glass of water, the water doesn't sit in the top of the glass with the air underneath, right? It goes to whatever the most stable configuration is, and it'll wiggle and wobble for a while, but eventually it'll settle down into a stable shape. Okay? Everything in the universe tends towards this state of stability, this lower energy state, and so these elements are no different. Fluorine is one step away from being more stable. Fluorine has 7 valence electrons. If it could just get one more, then it would be just like neon. It would be a noble gas. It would have a full valence shell. Okay? So how can it do that? Well, that's what a chemical reaction is. Okay? Another big star. Elements will, Okay, they will donate sometimes, or they will accept whatever they have to do. They will give away electrons, or they will take electrons in order to get that full valence shell. And this is the new thing for this unit. Okay, all along we've been saying if the element is number 9, then that has 9 protons and it has 9 electrons. Well, now you need to take a step beyond that. You see, fluorine can get an extra electron. There's a way that it can do that. Okay, and when it does, that's a chemical reaction happening. If I throw sodium into water and the water starts on fire, that's just energy being released when sodium is doing its thing to get a full valence shell. That's all a chemical reaction really is. Isn't that interesting that it's all electrons? Anyway, elements will donate or accept electrons to get to a full valence shell. Very, very important, okay? By the way, actually, I'm going to erase this. Side notes about this. A full valence shell is usually 8. And so this fact that elements will donate or accept electrons to get a full valence shell, this is called the octet rule. And of course that prefix OCT, oct, that means 8. Octopus, 8 tentacles. Octagon, 8 sides. Octet rule, 8 electrons. Okay, elements want 8 electrons. Only one exception, helium's happy with 2. Everything else on the periodic table is shooting for 8. Okay, so again, let's look at some examples of how this happens. I've been doing a lot of talking and you've been doing a lot of writing. Now would be a good time to pause and stretch if you need a little break, because I have to keep talking here for about 5 to 10 more minutes. This is a very important topic in chemistry. So go ahead and pause, take a quick break, stand up out of your chair. Okay, you've paused. I didn't pause. Let's keep going. Example. So I've just drawn 2 fluorine atoms right here. Each one has 7 valence electrons, and they're right next to each other, and this is the way it is in real life. If you have fluorine gas in a container, there are many atoms of fluorine, so there are lots of them next to each other. Well, look what happens if I grab one of these. Oops, didn't mean to do that. But when one fluorine atom moves close together with another one, look what just happened. Think about this now. As long as these 2 fluorine atoms stay together, this fluorine atom, look around it and count how many electrons are next to it. 1, 2, 3, 4, 5, 6, 7, 8. Interesting. It's got 8 valence electrons just like it wants. Look at this other fluorine atom. I'll do this one in orange. And if we count everything inside of this orange bubble, this is the first fluorine atom's kind of circle of influence, right? 1, 2, 3, 4, 5, 6, 7, 8 valence there as well. So as long as these 2 fluorine atoms stick together real close to each other like this, they're going to have 8 valence electrons, which is exactly what they want. Okay? So what we've done here is what happens in real life. 2 fluorine atoms can come together and they can share 2 electrons, 1 from each, and this will give them both what they want. Okay, so it's important to note that each fluorine wanted 1 more valence, right? They each have 7 and they want 1 more, so they each need to share 1, and that's how they each get 1 more. Okay, so this is called covalent bonding, and this is one way that atoms can get their octet rule satisfied, by sharing. Okay, co means shared, valent means valence. Okay, each fluorine atom shares with the other. And that's a really nice strong bond. Okay, I'm going to show you one other example of covalent bonding here. Sometimes they share more than just one. Like all the halogens only need one more electron, right? So they're all going to share one, and then that'll give them their 8 valence. But what about these right next door in the reactive nonmetals, oxygen, sulfur, selenium? They have 6 valence electrons. Can they get to 8? Let's look at oxygen, okay? So here's one oxygen atom. 1, 2, 3, 4, 5, 6. And here's another oxygen atom. 1, 2, 3, 4, 5, 6. And again, I'm going to play that game. What just happened here? I must have clicked the search. I'm going to bring them close together. And we're going to see how if they share, they will each have 8. But now they're each sharing 2 with the other. Okay, so here is one of the bubbles. 1, 2, 3, 4, 5, 6, 7, 8. And here is the other bubble. Okay, each shares 2 with the other, and now they still have the octet. Okay, so in the shared area, there are now 2 pairs shared instead of just 1 pair. Each oxygen atom shares 2. So that's covalent bonding. Okay. Ionic bonding is a different kind. Okay. This is real nice. This is 2 kids getting together in the sandbox. They each have a toy that the other one wants. And they say, well, I'll share with you if you share with me. And they play together, and they're happily ever after in the sandbox, sharing each other's toys. Well, we know that's not how it goes all the time in the sandbox, right? Sometimes 2 kids get together in the sandbox, and one kid sees that the other kid has a toy that he wants or she wants, and they take it. And then they run away, right? That's ionic bonding. Donating, accepting, stealing, however you want to take it, talk about it, okay? So here's how that looks. We're going to start with a sodium atom, and I'm going to draw the full Bohr diagram here. You'll see why in a moment. Sodium has 11 electrons. That's 2 in the second shell, and 1 in the outside valence shell because it's in group 1. And over here, I'm going to add a fluorine atom. And this one, I don't need to draw the Bohr diagram to show you what's happening, so I'm just going to draw the Lewis structure for fluorine. But you can see fluorine wants 1 more. It has 7, wishes it had 8. And sodium has 1 kind of an extra valence electron hanging out on the outside. Sodium actually wants to donate that 1 valence electron and put it right there, give it to fluorine, so fluorine has 8. When sodium does that, fluorine will be totally happy. But why would sodium want to do that? Why would sodium donate 1? Isn't it trying to fill up to a full valence shell? Well, you see, when sodium donates 1 electron, that gets rid of the whole 3rd shell. And what's left underneath is the 2nd shell, and look, the 2nd shell is full with 8 valence electron. Okay, donates 1, then the 2nd shell becomes the valence shell. See, it used to be the 3rd shell was the valence, but it got rid of that 1 electron. So when the 2nd shell becomes the valence shell, it's full. So by donating 1 electron, sodium is happy and fluorine is happy. Okay, that's ionic bonding. Again, just like with covalent, you can do this. Some elements will donate more than one, right? Let's look at magnesium. Has 2 valence electrons because it's in group 2. And remember, up above we did an example with oxygen. Oxygen has 6 valence and it wishes it had 2 more. Well, that's a match made in heaven right there. Here's an oxygen atom with 6 valence electrons. Magnesium just wants to get rid of its 2, and oxygen wants to take 2. Done. Magnesium oxide. Interesting how easy those names happen, huh? You can also donate and accept 3. In the interest of time, I'm not going to do that. There is a pattern on the periodic table. Okay. Group 1, Group 2, here's 13, 14, 15, 16. I'm actually going to have to fix this. Oopsie. So that it looks right. Then there's group 17 and 18. All the ones in group 18, they're happy. Group 17, they want to get 1 more, right? They have 7 valence, they need 1 more. All of these, that was supposed to say need, sorry about that, need 1. Everything in group 16, 6 valence electrons, right, needs 2. Everything in group 15, those elements all have 5 valence electrons. 3 more and they'll have 8. So these ones need 3. Group 14, those are right in the middle. Those aren't going to give up or take any. They don't know which direction to go. We did sodium was in group 1. Okay. Anything in group 1 is going to donate 1 electron. They all have 1 valence electron, so they're all going to do the same thing that sodium did with its 1 valence electron. Okay. Group 2 donates 2. That's magnesium. And finally, group 13 has 3 valence. They're going to donate 3. So you can tell right away just by looking at where something is on the periodic table what they're going to do. And so you can see from that this area right here where they need electrons, those are the nonmetals. Nonmetals accept electrons. Metals, they donate. Metals are losers. They lose their valence electrons. All right, I've talked long enough. This is all very important stuff, and I've given you a big overview of all of it. We're going to do more and more practice so that you get this down, but at least now you have an introduction to there are 2 ways for bonding to happen, ionic and covalent. Covalent means sharing. Ionic means donating and accepting. Okay? And the reason they do this is to get a full valence shell. That's called the octet rule. And that's it. That's the whole spiel. See ya.